we'll cover 3 examples of using mathematical induction. This video is so important to watch if you're interested in learning how to utilize mathematical induction. You can't just learn mathematical induction by interpreting the definition. Sure, it is extremely important to watch the last several videos on my introduction to mathematical induction, but if you don't go through examples of mathematical induction, you will be very lost, even with the amount of content I've discussed thus far. After this video, I hope that you will be prepared to construct proofs using mathematical induction on your own. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below and make sure to click on that subscribe button. Let's get started with our first example. We're going to prove for each natural number n greater than or equal to 1 that 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1, all divided by 2. First off, let's think inductively about this equation. In fact, we know this is true for other reasons. There's actually a clever trick you can do here. You can rewrite the sum n plus n minus 1 plus n minus 2 plus plus 2 plus 1. And then you add up term by term. It's the same list, just written out different ways. First one's going from 1 to n. The second row is going from n to 1. But they're the same numbers, same addition, and we're adding all the numbers together. You notice each of these terms is n plus 1, and we're adding up a bunch of n plus 1s, namely n of them times n plus 1. Or I should say, sorry, n times, well, you have it right here. It's n times n plus 1. And then notice we counted that the row twice. There's 2 rows. So we need to divide by 2 to get the total amount from 1 plus 2 plus 3 all the way up to n. So then we divide by 2 to fix that. So that's one explanation as to why this is. But why might induction be applicable? The left-hand side adds up the numbers from 1 to n. If we know how to do that, adding just one more term, n plus 1, would not be that hard. For example, if n equals 100, suppose we know that the sum of the first 100 numbers is 5,050, and it is 5,050. Now, to find the sum of the first 101 numbers, it makes more sense to just add 101 to 5,050. Instead of computing the entire sum again, we would have 1 plus 2 plus 3 plus all the way up to plus 100 plus 101. That would be 5,050 plus 101, which is 5,151. In fact, it would always be easy to add just one more term. This is why we should use induction. Now, let's go look at what the formal proof looks like. So we're going to let P of n be the statement 1 plus 2 plus 3 plus plus n equals n times n plus 1 all over 2. And so first off, we need to take a look at our base case. So we're looking at, in this case, P of 1. We're going to start by 1 because that's the key number here to start with for our base case. So P of 1 is the statement 1 equals 1 times 1 plus 1 all over 2. Is that true? Yes, it's true. It's definitely true. The left-hand side's 1, the right-hand side's 2 over 2, which is 1. So the base case is correct. Now let's look at the inductive step. So remember, the format of the inductive step part of the proof is that we're going to show that P of k implies P of k plus 1. And so we're going to assume for an arbitrary member k here, we're going to assume that P of k is true, and we're going to try to show that P of k plus 1 is true for this portion. So what is P of k? So we're going to first off let k be a fixed arbitrary member or element of the natural numbers, or you could just say it's greater than or equal to 1, either or. And let's assume that P of k is true. And you're going to notice through these 3 lectures that I'm about to go through for all of these 3 big induction proofs, you're going to notice that it seems like we're assuming the conclusion here. Again, we're not assuming the conclusion. We're assuming P of k is true for some arbitrary k, not all k, just some arbitrary k, so that we may prove that P of k plus 1 is true. And so for any arbitrary case like P of k or P of 1 or P of 2 or P of 10 or anything, you can then assume that the next instance is also true. So we're assuming that P of k is true. And so now we need to look at this statement for n equals k plus 1. So we're trying to show that, and I'll even actually write this out instead of before getting into consider portion here. We want to show that 1 plus 2 plus 3 plus all the way up to k plus k plus 1 equals k plus 1. Actually, I could probably fit that. Maybe I could fit that. Times k plus 2 all over 2. Since my n is k plus 1, that's n times n plus 1. So we want to show that's true. Now we know that P of k is true. That means that 1 plus 2 plus 3 plus all the way up to k is k times k minus 1, or k plus 1 all over 2. We know that's true. And if that's true, then this should be easy to prove because I know what 1 plus 2 plus 3 all the way up to plus k is. It's that. So 1 plus 2 plus 3 plus k plus 1. Well, this portion right here is just k times k plus 1 all over 2. And then I have left over here plus k plus 1. And I can rewrite this right here as a fraction. So this is k times k plus 1 all over 2 plus 2k plus 2 all over 2. Let's see if we can keep going here. That's equal to k squared plus k plus 2k plus 2 all over 2, which is k squared plus 3k plus 2 all over 2. We can factor that top as k plus 1 times k plus 2 all over 2, which is exactly what we wanted to show here. We started with this expression, we simplified it using our inductive hypothesis, and we showed that that expression in the purple box is this right here, which is exactly what we wanted to show. This is P of k plus 1. And so that means that by induction, P of n is true for all n greater than or equal to our base case, which in this case was 1. And that's the proof. Anyways, thanks everyone, and I'll see you in the next lecture.